So in the last optical flow, we calculate by checking the similarity image, and we check where the patch has moved. So we took a one patch and it moved somewhere, and we try to measure it by checking similarity image. And now we try to do it in a different method, and this is called uh, the name of this method. Let me see. Um, I guess Saul knows the method.
Lucas Candy.
Yeah. Lucas Kanade method. And in here, the starting point of this, what is velocity? If you take the first derivative by time of a distance, so you have this distance, let's call distance as s. And if you take the first derivative by time, you get velocity, right?
Velocity.
This, this equation.
Distance
Yeah.
equation.
Yeah. So no need the equation. So if we take the distance and if you take the first derivative by time, so you get velocity. What if you take the second derivative? What you get?
Acceleration.
Acceleration.
Acceleration. Okay, this is our starting point. And now we are looking at two displays, and this velocity and the distance, it could be on two direction, could be on x direction and y direction. Okay.
Yeah.
Yeah.
Hello.
Yeah.
Can you hear me?
Hello. Yeah.
I thought I think I mute my mic.
Okay.
What did you guys? I mean, when did you hear me for the last time?
That acceleration and velocity.
Okay. Now it's a 2D image. In the 2D image, you need to calculate the velocity on x direction and y direction. Okay.
Hmm.
The total velocity, let's say the velocity in this direction, that is equivalent to you need to take the velocity on x direction and y direction. Okay. That's mean you need to take the derivative by time by x direction and y direction. This is same like in maths we did some equation. We took the derivative by x and y. So it's the same thing. The reason is we apply this one practical now. And in the 2D image, if we need to find the velocity in here, so we need to take the first derivative on x-axis, and we need to take first derivative on y-axis. Okay. So this is understood, right? Okay. Then we can write this equation.
And y transpose?
It's a good
This
question.
T?
It's a good question you ask. I don't know the reason exactly why we take the R transpose in here.
Okay.
Yeah. But
Where did you get this one?
it's from the equation 12.93. in the book.
Oh,
Yeah.
okay, let's continue.
I guess this the transpose in the sense in here, the vector, it should be like this long vector. It doesn't say anything more than that, because you get a velocity for x, you get a one value in here, one value in here. So, but it's not that important in here.
Yes, let's continue.
Yeah, we'll continue. So let's draw one function like this, and if you need to know the velocity of this function, so then we need to take the derivative. And in the video sequences, there are three things. Let's take if it is a video, so you have x and y and time. There are three components. Okay. And let's say you are sitting in this point, particular point. Okay. That means you have three components, time and y and x. And if you need to predict the next one, okay, how you do it? If you have this, x derivative and y derivative and t derivative, you can add those particular change in time for a particular point, and you can predict the next guy, right? That is what we had done here. So you multiply with your derivative. It's same like, this is the same thing like we take the derivative of f. So let's say we have the f function and it has the x and y and f time. So we took the derivative by each component, by time, by x, and by y. We need to find the change in the time. Then the next step is, if we want to find how much df has changed for a particular time unit, then we need to divide everything by dt, because dt is for the time, right? This is for the whole time. And but if you want to find the changes only for one particular time unit, because why I'm saying particular time unit, in the video, the frames comes one after another every 40 milliseconds. So 40 milliseconds is our time unit in here. So if you need to calculate the changes between your first frame and the second frame, then your time unit is 40 milliseconds. Okay, your dt is 40. Okay, then there's something. It's called brightness constancy constraint. What that is mean? So let's say you have this patch, this image, and after 40 milliseconds, you have another image like this. And if you want to move some patch, for example, now after 40 milliseconds, you have another image. So there's one. Let's draw something in here in red color. There's a small red patch. In the next image, red patch has moved to some corner like this. So if you want to track this red patch to where it is moved, so we need to see, we need to consider the brightness of the image. It didn't change. Let's say the pixel value has a brightness of 128 in here, and what if the pixel has a brightness of 200 in here? Then we cannot calculate anything, because all the pixel value has changed, right? But when the object has moved only across these values in here and here, brightness values should change, and all other values should be constant. So that's why we have this BCC brightness. We think the brightness is constant after 40 milliseconds. Practically, it should be, right? You got it or not, guys?
Yeah, got it.
Yeah, got it.
Yeah. So let's say for a moment, you have one image here, and after 40 seconds, you have another image, and nothing has changed. The patch is not moved. That means the brightness didn't change at all. If the patch is moved, at least in this particular area, brightness will change. Because the new point become darker, and the previous point become whiter. But if the patch is not moved, this equation, the change on next time frame, it is 0. there is nothing, no change. Okay, that is what it says in here. And in here, dx by dt, we already said what is this? The velocity by x. And dy by dt, velocity by y. And this term, yeah, it is the same term it came here. So the change by time, the function change by time, it is 0. There is no change. So that's why this is become 0. That's the interpretation of that. And this is our starting point now. The second starting point, 1297. Okay. This is our raw function now. So based on this only, we will do all the calculations. Okay, is it clear so far? Now, just like the previous time, we have some unknown things and known things. Okay, in this equation, the velocity is the one we need to find. What is velocity? Like, you have a small patch in here where it is moved and in which velocity. And when I draw this vector, it has two values, and x and y. So that's why you have x velocity and y velocity. And these are the ones we need to find, and this is unknown. And the known things, the change in x direction and change in y direction, yeah, we can find it. Derivative on x and y. Oh, sorry, this is not derivative in x and y. Since it's known, just a minute, guys. Yeah, we can find these things. We can find these guys. Yeah, it comes on the next one. Df by dx. Df by dt, I can explain what this is. So let's take an image now. Okay. And after 40 milliseconds, you have another image. So in the video sequence, this is after 40 milliseconds. So this is change by time. How to calculate the change by time between these? This is the most simple one. This is the time 0, and this is time 1. How to calculate the derivative, the change by time? When you take a derivative, that means you are taking the change.
Derivative.
Yeah. So you can simply do it without doing any complicated math. You can directly take t0 minus t1. It's a difference, right? The image, how much it changed from here to here. Okay, after 40 milliseconds, you can directly take the first one and minus second one. Okay. But when the image has moved to some other location, you cannot do it like that way. Okay. So then we need to use derivation. And take a pixel in the image. So we do this derivation for each and every pixel. So we take the pixels and we take the derivation by x direction, and we take the derivation by y direction, and we can find these. And time. So the time, we don't take the derivation. What we do is, we just do the subtraction between two consecutive frames. Okay. So, but we need to wait for another 40 milliseconds. We can, for these derivation, we can directly take it, but to calculate this one, we need to wait till the next frame comes. Okay. So now the whole thing, there are two unknown things. This is unknown and this is unknown. Sorry, this is unknown and this is unknown. And there are known things. These three values are known things. And we can write it as a multiplication of two knowns and unknowns, like this. So what we can do is the same equation. So I can mention this guy as D. So So I can move. My pen is not there, so I will just write this guy as D. And other two parts, I can just directly move this into the other side. So I can, I will try to write it df by dt. And other side, I can move both of these the other side of the equation. So it becomes 0 Vx and this part, and I can put a big minus here like this, and plus Vy and other part. So this is it clear, this one? So in simply what I did was, this guy, I keep it here, and other two, I moved to the other side of the equation. This is a 0, right? So these two terms, I move other side of the equation. Okay, and then what I have two values, Vx. So for the other side of the equation, let's try to write it in here with my pen. Oh, gave me a hard time writing. Okay. So one side of the equation I get Vf dt equal minus Vx. Oh, it's very hard to write. Something has happened to my writing pad. Df by dx plus Vy df by dy. So is it clear, guys? It's the same thing.
Yeah.
Okay. Now this part I can write it as multiplication of knowns and unknowns. This is we did multiple times, guys. You should know it by now. So the knowns, df by dx and comma df by dy. This is one thing, and other one I can write it as a long vector vx and vy. Just multiply it and see. You will get the same thing. Multiply this guy with this, and this guy with this. So it's the same thing, right? So this part I can replace with this. Okay. And this part I can write it as D, and this part I will write it as V. And this whole thing, there's a minus term. So I can write minus dV, right? And let's write this part as small d. Okay. This is how the equation comes, but there's one more catch. But is it clear up to here before I tell the next thing?
Yes.
Is it clear?
Yeah.
I need clear. Is there any doubt you ask? Nima, is it clear?
Yes, clear.
Yosme, is it clear? Shabi, is it clear?
Yes, yes,
Clear,
yes.
Guru.
Okay. Now, there's one more catch. If you see a capital D or capital letter, that means it's a big matrix. You remember AP equals 0 and BM equals 0. And always, if there's capital, it's a big matrix, and a small letter in the sense, it's a vector. The thing is, I said in the image, we need to do this calculation for every pixel. This equation, we will do it for every pixel. Okay? And this is for one pixel, guys. My computer's doing crazy things. I don't have any control. Okay. So this is for one pixel. So what if we calculate for many pixels? So like this, we will get many terms, one after another, like this. So I'll get a very big matrix. How many pixels have I? If I have 1,000 pixels, I'll get a 1,000 by 2 long vector, very long vector, like this. Okay, this is how we get the matrix. You guys understood? Okay, and this is our Lucas Kanade equation. This is the starting point for that. Okay, but here, up to here, you guys understood? Or is it confused? But in the exam question, but I cannot remember any of these. But you guys remember, did the math comes or not?
This equation, this matrix was there. Big one.
A big matrix. Okay, okay.
I think we have the photo of that question. I'll see tomorrow and I'll ask.
Okay. So Now the thing is, we multiply both sides with D transpose. Why we do that? When we multiply this D transpose in here, we get a square matrix. So we had let's say it's 1000 pixels, so it is 1000 by 2, and other side also, then 2 by 1000. So we get a big matrix, 1000 by 1000 big matrix. Okay, so we get a big matrix in here. When we multiply, we get a square matrix. And other side, this is a D, it's corresponding to time. Okay, and now we can the D by D, it is same as structural tensor. So if you take the structural tensor, it is like this. And when you multiply structural tensor two values, what one structural tensor if we multiply the gradient of f with gradient of f transpose, then we get the structural tensor. So simply D transpose multiplied by D, this is what we are getting is structural tensor in here. Okay. So we will continue. Nima, when I send you the notes, don't go to this part, the pencil part in here 100%, because I'm not 100% sure. I just, expand this part and try to see the D multiplied
But
by
I
D.
have not in this part, only the part 2 I have. But
Yeah.
in this
No,
section,
no, I didn't send you yet. I will send you tonight when we discuss. Yeah, I will send you, because now
okay.
today only, like just before this video call only, Zoom call only, I just finalized this note.
Okay.
Okay, so now what happened was, stereo vision is more harder than this. Then I put a more effort for that, and for this one, I didn't even prepare the notes. Okay. Now, now our final thing is we need to find V, and how to find V? I mean, this is our final equation. Then we need to move this part to the down. So that's mean we get D transpose D divide by minus this part comes as division, right? Then we can put it as inverse and we can take it up. So this is how we can find V. So this is like from here to here, is it understood? So no, it's simple one, right? Yeah. So now there's one thing. To solve V, we need to invert D transpose D. See, we need to take the inverse of this. But we cannot invert a matrix if there is any eigenvalues are 0, then we cannot invert it. We previously also we discussed, right? If there is a eigenvalue is 0, then we cannot invert a matrix. Okay, and how this happens? If you take the linear symmetry patches, then its eigenvalues will be 0. One of the eigenvalues can be 0. So let's say, for example, this is the image, and one part of the image you have these kind of line, and other parts it's like these patterns and dots and things. And if you mistakenly take this part as your patch, so you have this linear symmetry line, and if you have these linear symmetry lines, then one of these eigenvalues will be 0. Then you cannot invert the matrix, you cannot do the exercise. Okay. Okay, just read this part and try to understand for first 3 points. And just confirm me whether you understood or not. So one of the key thing. Shabish.
Yes.
Yeah, read it. And Nima, is it clear? These 3 points. Shabish, is it clear? These 3 points.
Yes, yes.
Yeah,
Okay.
3 points understood.
Yeah. Okay. Then we'll come back to here. This is something in the structural tensor in the lab. When we calculate this capital S D transpose D, it's equivalent to these M values. And this is nothing but uh, okay, I can open this. It's same as this. So it's mean taking the uh, second derivative by x and taking the second derivative by y and taking derivative x and y. So we have three dimensions. First thing is x, fx, and y, and time. And the first element, it's corresponding to x, and this is corresponding to y, and third one corresponding to time. So M200 in the sense, you take the x double derivative. Then Nima, you tell me what is this?
Uh, mm,
It's
is it IY?
no, it's you take the derivative by y
Derivative of y.
two
Mm.
times because
Hmm.
first
Oh,
one corresponding to x, and second one corresponding to y, and third one corresponding to time. Okay.
oh.
Then somebody tell me what is this M110?
First with X and first next with Y.
Yeah, yeah. Okay. So remember how we construct. I remember there was one question. They asked what are the values for m. So the first value should be x double derivative, and second value should be x and y, and the last one is uh,
Derivative of
y double derivative. Okay.
Hmm.
So if you remember like that way, no need to remember M200, M02, no need to remember. But just remember the concept, then you know it. Then when the question gives like this or this way, okay, then you know what to do. Okay. And there's one more thing. When you multiply dt with d, we call it as b. B value is actually, when you compute it, it's like this. It should, because the b, sorry, the small d, this is comes from the time, derivative of time. Okay. And the D matrix, how D comes, it from the X and Y. So can Sonu interpret this? What is M101?
101
X,
one
Y.
with X and Z.
and t.
X and T. Yeah. Naveen is correct.
Okay, X and T.
The
Mm.
first element is X and Y
Oh,
and T.
mm.
So
Okay,
yeah, take derivative of X and
Oh,
time. Okay.
T. Hmm.
Okay. Nima,
mm.
tell me this. Nima is sleepy. Okay. What is
Little
M01?
bit.
Yeah.
Y and
M01.
T.
Yeah, Y and T. Exactly.
Oh,
Yeah. Then to solve this, to solve it, there's a
Hmm.
small trick. Uh, uh, because this is how we need to solve the. This is B, by the way. B by S. So there is one division like this. It's actually in MATLAB. It's called Gaussian elimination technique. Uh, because if you try to divide by this, it's very hard to get the answer. So that's why they use Gaussian elimination technique. I don't fully understand that, but that is the explanation. In the MATLAB, we do it like that way. We use this division. Okay. And this is the same thing I said. Nima, just have a coffee.
no.
Okay.
It's
Then,
okay.
okay. So taking derivative by time, we don't actually take the derivative by time. We just subtract the current frame and the next frame. Because what is the derivation? Derivation in the sense you check the differences. You take the change, right? What is velocity? Change of distance. And change of time, you can directly subtract one frame from another. Okay, that is how you do it in an easy way. But the thing is, if you do that, it makes some artifacts. If you don't do a proper derivation. So you guys remember how we took the derivation in image analysis? We took the derivation, then we use a smoothing filter, Gaussian, some kind of interpolation function. You guys remember what is interpolation function? Anybody? Shabish? Sonu?
No.
Okay.
Multiple by multiple, not the sum.
Uh, come again?
No, I mean, it's the like, how to explain that?
It's averaging actually. So
It's yes.
let's say you have this discrete signal, and you want to create a continuous signal. When you use the interpolation function, what happens is it smooths these edges and it creates one continuous line. So I'm just trying to find say it in a very simple way. So it's just like a smoothing. Okay, you have some kind of a smooth brush, so you're just smoothing this. Okay, so every position you apply the interpolation function like this. Then when you multiply with the interpolation function, you get a smooth curve. This is what the interpolation function is doing. So when you take the derivation also, you first take the derivation on the particular axis. For example, let's say you are taking the derivative on x-axis. You take the derivative, then you apply the interpolation function. Okay, and if you take it like this way, there is no interpolation function. It makes some problems. So what we do is we artificially multiply with 1 and minus 1. 1 and minus 1 is nothing but it's a derivation of the interpolation function. Usually for the interpolation function, we can use Gaussian distribution. Normal distribution. It's like this. So it's called Gaussian distribution. And derivation of a Gaussian distribution, it's for this part, the first part, it comes a plus, and for the second part, it comes a minus, because this is the plus acceleration and there is a minus acceleration, and you get like this. So that's why you multiply it with plus and 1 and minus 1 with your first frame and second frame. Okay. Okay. So there's something like in the lab, what we do is like previously for the patch, what we did, we check some area where the patch has moved. But in now, we will calculate these values, derivation for x-axis, derivation for y, derivation for the time, for every pixel. So these images, the images has RGB 3 values. But right now, we will, our image has 3 channels, RGB. So we will make 6 channels. And what are the rest of the channels? It's a derivation by x, and derivation by y, and derivation by time. And for every pixel location, we have RGB values and derivation by x, derivation by y, derivation by t. Then for any given time, we can just cut a piece and we can try to estimate the velocity. But when we take a piece, we need to see if one of these eigenvalues becomes 0, that means it's not a good patch. So it's linear symmetry. So it may have some linear symmetry lines. We cannot use it. Okay, you guys got it? So that's why it's
Yeah.
mentioned. Calculate the structural tensor. Check for if there's any 0 value. It's not a good patch. Okay, so I'm just trying to go fast because you guys are sleepy. So so this is called Logos Kanade or feature tracker. So in reality, we can use this for track a pixel movement or color movement or like a heat map instance. That are infrared cameras. From that infrared cameras also movement we can track it. He can ask what is Harris corner. It's been lack of direction. Lack of direction is I said we will calculate this for every point, and there could be some linear symmetry. So this is lack of directions. So Harris corner in the sense it's nothing but the bad patch. Okay, remember like that. Okay, because he may ask these kind of things. Optical flow can be calculated insert images. Okay, so one more thing is there. If the movement is small, then we can calculate this easily. If the movement is very fast, it's very hard to calculate. So what we can do is, you guys remember Gaussian pyramid? Gaussian pyramid technique we use to downsample image. Simply we can make the image smaller. For example, I have big image in here. Okay. Now there's one movement from here, and next frame it's moving this much. Okay, it's a long distance, very long distance. So it's very hard to track. So instead of that, what we can do is we can make the whole image smaller. And now the movement relatively it's less
Sure.
pixels, right? Size is small.
Okay.
So we can
Mm.
calculate it. So there could be questions like that. So if it is hard to calculate, yeah, we can make the image smaller. So how to do it? Make the image smaller. You remember the Gaussian pyramid? We can say downsampling in the sense of making the image smaller.
Mm.
So the Gaussian pyramid concept, we had something like, we make it smaller, like a pyramid. The top, it goes smaller. It's from the image analysis. So he may relate these words, just remember. Okay. Okay, now how to take derivation. So we can use this convolution function to take derivation of an image. So if you want to take a derivation of particular direction, then you need to apply your derivation, your smoothing function, and your image name, and same in the sense you give you give an input and your output also same size. Because when you usually apply convolutions, what happens is image becomes a little bit smaller. So we can prevent it by adding uh, paddings, zero paddings around that. Okay. Well, it's not a big thing to remember. Okay. But remember, our RGB, so what this says, our in RGB image, we have only 3 channels, but we make it another 3 artificial channels. So derivation for X, derivation for Y, and derivation for time. Then we take patch from anywhere, and then we can calculate the flow. Okay. Yeah, that's it. Then we can go to the lab. But guys, is it like you got anything or how? Or is it too fast? Oh no?
Yeah, got it.
I guess it's a little bit fast. Shabish,
Lab.
you are awake?
I think
Yes,
Shabish is
yes, I'm
sleeping.
back.
Okay, not sleeping, right?
No.
Okay. In here, so I will start with this gradient, and I will run this, and I will ask you one thing. Now these images are moving. I guess I can make the speed higher by E. And this is actually dy. This should be dx. Okay, I will write the correct thing. This should be dy, and this should be dx. And the y direction is like this direction, right? And for these patches, y direction. Wait. Mhm. The interpretation is and y. if we take the derivative of this axis, we should see the maximum changes. What's the problem with this? No, I cannot explain this right now. So, because in the lab we notice this is not dx, this should be dy, and this should be dx. If that's the case, my explanation doesn't work. Maybe this is the corrected code. I need to check it. But one thing we can do is how to take the gradients. I can show you in the code. There was one question it asks how to take the gradients. You guys remember how to take a gradient of image?
No.
Yes. It is stuck. So it doesn't want to open. I will close this and okay. I'll stop this and see. Okay. Gradient tree. So I can stop this by somewhere around here, and I will run this. Then I will come back and explain. So okay, so I will run this file. Okay, there are some function called make filters. This is taking some Gaussian filters. So you remember normal distribution Gaussian like this? Okay, this is a Gaussian distribution. So in the Gaussian distribution, how we identify the corners, we should have lower values, and the middle we should have higher values, and the down next corner we should have lower values. And when we take a derivative of this, so you tell me what's acceleration in here, plus or minus? Here, this part.
It's increasing, right? So
Yeah. Plus acceleration. And what about this part?
decreasing.
Yeah, decreasing.
Minus.
When you take the derivative of this curve, so the derivative is like acceleration, right, on this curve. So we can write it like this, the plus curve. So acceleration from here start with a high value, and here it becomes 0. We start with acceleration 0, and middle we get the highest, and it is 0. So when we draw the derivative, it comes to a highest and again goes to 0. And here it's a minus. So start from here, 0, ending with 0. In here comes to a minus highest. So this is the derivation, plus and minus. And now we look at these filters. We get it from this. We are directly getting the filters from this command. And GG, is it a Gaussian or what? We get 3 values, but by looking at this, we can say, okay, it's a Gaussian distribution. We have 2 values, and middle we have higher value. Okay, this is a Gaussian distribution. And what is this then? It's a derivative of the Gaussian distribution. So it's simply, okay, Gaussian distribution is our interpolation function. Interpolation function is the filter of the convolution. Okay, so we have 1/3 filter now as a Gaussian distribution, and also we have a 1/3 filter, the same one, the derivative. So this is the GG is our Gaussian, the interpolation function, and GX is our derivation function in the same one. So in the image analysis, what we do is, instead of taking the derivative of an image, we take a filter interpolation function and take the derivative of the interpolation function and do the convolution. Okay. In this way, we can take the derivative of the image. So I repeat, if you want to take the derivative of an image, what you do is you take the interpolation function. In here, it's a Gaussian, and we take the derivative of that, and we do the convolution. We use this one as the filter in the convolution. Okay, is it clear to you guys? I need yes or no. This is from the image analysis. Last tables.
Ah, yeah, yes.
Yeah. Okay.
Understood.
Remember? Somebody remember? Sonu sleeping in the class.
No,
Okay. Shabish didn't attend the class. Shabish, you remember this?
Which class?
Which class? He doesn't know. Last year image analysis.
I came.
Okay. Naveen, yeah, he doesn't know because it's 1 year before.
Yeah.
Yes.
I don't have any
Because
idea.
Naveen enjoyed 1 year back in India.
Memory loss.
Memory loss. Okay. But at least Neo remember. But now you guys got it, right? So this is the same thing we do, but one more trick is there. You guys remember, uh, when we do the convolution, instead of applying a 2D filter, we can apply two 1D filters, and that is more efficient. So one thing is, for this image, we can apply 2D filter. And second option is, we can apply two 1D filters. One filter, like let's say your original filter, 2D filter is 3 by 3 filter like this. Okay, this is from the image analysis last course. Or we can apply uh, two 1D filters like this, one after another, like this. Okay, so if you use this way, it is a lot more efficient. Okay, so right now, while doing the convolution, we use two 1D filters. Okay, there was one exam question also. Okay, so you guys got the trick, right? So I'm trying to move forward now. So in here we took the two filters, and this is one function. Take the previous image and I guess taking pixel by pixel, but we don't do any convolution. We do the convolution in here. Okay, so we take the image, and this is our GG filter. But we actually take the IUI and everything in here. Okay. Just a minute, guys. Okay, so we take the image in here. And how I by is nothing but taking the derivation by y direction. Okay, and gy. So this is our derivation filter, and this is the interpolation filter. So what we do is we take. You can see this is the derivation filter. By looking at that, you can see plus value 0 and other part is minus. And gg, this is your interpolation function. So you apply the, the derivation followed by interpolation, but derivation followed by y-axis and interpolation followed by x-axis. Okay, this is how it is done. Okay, and by the way, this is two separable filters. You take the convolution with two filters. Okay, guys, you got it?
Yeah.
Okay. And for the x, taking derivation of x, so what you do is you apply two separable filters. So you take the derivation of this derivation, and interpolation on other direction. Okay. Then to the time, taking derivation of time, we just subtract the new image in the previous image. We don't actually take a derivation. Okay. We just subtract from first one from the second one, because it's a change in the time, and that is how it is calculated. In here, just get the idea. We use two separable filters, and yeah, use the convolutions to do that. Okay. Then I will go to the next one. Then we need to use LK method. Now we try to calculate the optical flow for the real one. In here, it is do flow LK. Yeah, it is this one. So I will keep some. I will. And I will run the file. Okay. So guys, now we need to calculate a couple of things in here. We need to calculate this S vector. Okay, we know if we calculate this structural tensor and B, with this way we can calculate our velocity. Okay, and if I keep these values side by side, no need to keep side by side. You guys know by looking at this. What is M020?
Double derivative of y.
Yeah, double derivative of y. Okay, so let's see whether it's double derivative of y. So how you take the double derivative? You have single derivative. So you take the square. So you multiply the same one with same. And what this means, point-wise multiplication. Okay. So if I take my, it's like, this is the derivation not for a single point. This is for the whole image. Dy, let's see what is our dy. Yeah. This is for the whole image we do it. Okay. For every point, we calculate the double derivative. Okay. And followed by, for the side of x, it's a Gaussian filter. This is two separable filters. That's the same thing. Okay. And can somebody explain what is this?
xy.
XY. And what is this Sonu? Hey Sonu. Sonu is sleeping.
No, that is derivation with x and time.
Okay. Shabish, what is this?
Y and T.
Yeah, Y and T. Okay. And this is, can somebody explain me what is this? Nima?
Derivative of x.
Derivative of, double derivative of x.
Double derivative.
Okay,
But you know, he could do it in the same way, but he tried to, divide into 3 steps just to explain us better. But it makes us more complicated. I mean, this is too complicated, but if he write in here, it is more easy to understand in a single line. So he can write the same thing like here. You can directly write like this, dx square. So it should be here dx and dx and g and g. So if you write like this, that is more easy to identify. Yeah. Anyhow, so we calculate our m values now. Okay. Then when we calculate our m value, by the way, guys, how we calculate? We take the derivative by x and y for the whole big image. Okay. So that's why when you take the derivative, when you take the derivative by x direction or y direction, I mean, our image is 128 by 128. So we take the derivative of the whole image. Okay, that's why the derivative, if I bring my mouse point here, you can see 128 by 128. So we took for the whole image. That's why. And for every position of the image, now we have multiple. Other than RGB values, we have another what do you call it? The channels, the x derivative channel, y derivative channel, and time derivative channel. So for this, now we construct the structural tensor. Structural tensor, it should be x double derivative, and here y double derivative, and x and y, and x and y. And also we need to construct this b. The construction of b, it is in here. It's x with time and y with time. So we have x with time and y with time. Then this is the easy way to solve it. To finally calculate the velocity vector by rotation between vector b. So, and we use this trick. Okay, then we get the velocity of y in the v vector. It's a full vector. We should have two directions. Let's see on the second row. Oh no, it doesn't calculate. You know what this is? Can anybody answer what is this? I put a comment. This is to check if any of these values are zero. Guys, if any of these values are zero, then we will not like calculate the velocity. So, but you know, some cases he gave this epsilon value. If the values are smaller than 0.3, I mean, he used this recon method. To identify if the values are too small, comes to zero, any of these eigenvalues, then he will not calculate the velocity. Because if the values are zero, then we cannot invert this matrix. Okay, this is what we are checking. But you can see now, we'll see typing in here. Okay, you can see some values are zero. So we cannot invert. So no, you are awake? So no, you are sleeping?
Yeah, no, I'm here.
Okay, so you can see some of the eigenvalues are zero. And that's why the for loop, when I run it, you know, the for loop doesn't go through this middle section. See, it directly jumps. The reason is, if we take this one, now we start from one of these corners and we calculate the, you know, for all of these pixels, we calculate the structural tensor. But you can see all of these points, there is no pattern, all of these points. So it's like, you know, linear symmetric. It's just a plane, empty plane. So that's why we get zero values. But if I run this to the end, let's see now. So if I try my M200, yeah,
Hello again.
yeah, can you hear me?
Yeah, I'll just go for picking ships here now.
Okay.
The work finished. So she called me. So I'll see this lab and I'll ask if any doubt is there.
Yeah.
How
But
much time will be there?
if you
I
can just
think
wait
10
for like another 2 minutes, yeah, just wait for another 2 minutes.
Okay, then I'll
It's
see
done
it.
actually. It's
Okay,
already
I'll
almost
just
done.
get into the car and I'll listen.
Just wait 2 minutes.
Okay.
Yeah. Guys, I think I modified the original lab, so that's why you're seeing it like this. Okay. Guys, it's the lab 2. Okay, then I will run directly. Just I can show the output. Oh, so this just me, guys. Also, originals, completed files. Okay. Okay, now it's working. So now we can see these arrows. This is the velocity. So velocity estimation, we could properly do only this check pattern, and all other cases we couldn't do it. On the previous lab, remember, so I'll just stop this now. So in the previous lab, we could even calculate the velocity for these, the displacement. And only we couldn't do it for these two. But in the exam question, if there's anything, but in this method, Lucas Kanade method, we can do the proper estimation only for these check patterns, because this is a linear symmetric pattern. Okay. And this is also kind of a linear symmetric. And this is, yeah, obviously it's linear symmetric. So remember this, he can give some different patterns, like, if you have these dot kind of patterns or bubble patterns, only these places we can calculate. Even for these, we cannot now. Previously we calculated, because our rotation in this way, now this is orthogonal rotation direction. So we could calculate earlier, but now, no. Okay. But the advantage is, now previously we got the directions like this, and here directly like this, and it wasn't smooth, but now it is very smooth. Yeah. The reason is, previously we compare the patches around that, so we need to find exact matching patch. If we don't have enough resolution, we'll not get enough good movement. So but now there is no problem like that. See, you can get this, because we get the velocity exactly in the round motion. Yeah. Okay, that's it. Okay.
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 Finished.
Yeah, finished.